Last week we done a little bit of a revision really on how to resolve particular functions into partial fractions, and the reason for that was what we're going to do this week is to look at how we can integrate using partial fractions. So that top problem there, if we consider the problem solving that integral 11 minus 3x over that quadratic, there isn't a standard entry in a table for that, in your table of standard integrals. But what we looked at last week was how we can resolve that into partial fractions that are equivalent to it. So this function here. Can you see a way, without looking in your notes on the next page, because I haven't given them to you yet, can you see a way that you could actually integrate that function now? Any ideas? Remembering that if we've got two functions separated by a minus or a plus sign, we can integrate each of those separately. Sorry, Catherine? Yeah, we can use substitution on each half. So we can do substitution on that half, substitution on that half, and get a result, and then that's the result of that half taken away from the result of that half. Okay, so we'll have a look at how we can do that now. So can we remember how we do integration by algebraic substitution? If we look at this half first, the integral of 2 over x minus 1 dx. Just pause that for a minute. So that's that side. We then just need to do this side over here. So we've got the integral of 5 over x plus 3 dx. Process is that u equal x plus 3. Okay, off we go, finish that one off. And Alex. Yeah. One, yeah. Therefore, we've got to rearrange it. Yeah. dx equals du. We maybe don't need to write this out so many. Sorry? Yeah, what, like that. I read it all out that time just to show the process, really. So we're now, therefore, we're integrating. What was it? 5. Take away that one. So the final solution is 2 ln x minus 1 minus 5 ln x plus 3 plus c. You're going to have an extra point if you only included but you have and a plus c that all together as one constant of integration. Hopefully I've not gone wrong there any. But are they constants in each of these solutions? Well, I don't think you do, because if you wrote that out as 2 ln x minus 1 plus c minus 5 ln x plus 3 plus c, the two unknown constants you would just bring together, wouldn't you? They're both different. Well, if you had data to give you a particular solution, then you found a particular solution of 2 halves separately, you'd have 2 separate constants, but they'd still become one constant in the end, wouldn't they? I get your point. That should be pointed out why they join together, but they do. Yep. Everybody happy now? Okay, so what we're going to do now, and we'll do the first one together, because in that first example I gave you the partial fractions. So now what we're going to do is join together what we learned last week with what we're trying to learn this week as well. So I've put in your notes, I've put these on separate pages, so you've got room to do working as well. But we're going to have, for the rest of the session, have a look at solving these three integrals that involve partial fractions. Okay. We'll note that at this stage I've already factorised the denominator, so you haven't got to worry too much about the factorisation. So let's have a look at this first one. Where do I start with integrating the function 12 over x plus 3 times x plus 3? We did last week. So we can say that is equivalent to, guys, partial fractions, like only 7 days ago. I over x plus 3 plus b over x plus 3. Remember that. Oh, 1's minus 3. Beg your pardon. It's part of my deliberate mistake. Do you get that, Brenda? Are you happy now, Jack? Yeah. Right. What do we do next? What we got to try and achieve that we've got over here, a common denominator. So what we want is that common denominator back. So what would you have to do to the a fraction to get this common denominator? Multiply by x plus 3. And what would we have to do to the b fraction to make it same as the common denominator here? We've got x plus 3. We need to multiply by x minus 3. Yeah. Next step, equate the numerators. So we say 12 is equal to I x plus 3 plus b x minus 3. Then what do we do? Change colours for this. Yeah, okay. Which one do you want to start with, Jack? X equals minus 3. What does that do, Jack? It gets rid of the a term because a, it will be a times minus 3 plus 3, which is a times nothing. So this term disappears. We can then say, therefore, 12 in that case is equal to b times minus 3 minus 3, or b is equal to 12 over minus 6 equals minus 2. I'll go over this side. What do we have to do to get rid of the b term? Let x equal plus 3. So then we have 12 is equal to I 3 plus 3. So I is equal to 12 over 6 equals 2. Yep. So we got the constants I is equal to 2, B is equal to minus 2. We put them back in this version up here. So we put these two constants, I is 2, change that to a minus sign, because B is minus 2, like so. Can we now do the integral of 2 over x minus 3 minus 2 over x plus 3 dx. Okay. Which requires us to use substitution twice.